now I want to talk about impedance. Impedance is quite important because it tells you the ratio between electric field and magnetic field. And if you look into a circuit, it means the ratio between voltage and current. So we want to find out the relationship between the two variables, and we talk about surface impedance on a piece of conductor. And let's look at the definition of the impedance. The intrinsic impedance for a wave is defined through this relation. And if you divide electric field to the magnetic field, then you have a value equal to square root of mu over epsilon. And we call this intrinsic wave impedance. And we can also do the same calculation for a wave penetrating a piece of conductor. And we already figured out the epsilon value for a good conductor. That is equal to this value. So let's just put this value into this expression and calculate the ratio of electric field to magnetic field. Then we end up having this expression. Again, this 1 plus Ga comes from the square root of Ga in this epsilon. And so immediately you can write into a phasor form a complex exponential. Therefore, you have a phase difference between the electric field and magnetic field. And this phase difference is the pi over 4 or 45 degrees. So it's quite interesting that there's a phase difference between the electric field and magnetic field inside a piece of good conductor. And this could be understood from the fact that the electric field entering a piece of good conductor will spend some effort and also time to interact with the electrons. But the magnetic field will not see the electrons because the motion of the electron appear to be quite slow. So the electric force is much stronger than the magnetic force. So the electric field is going to fall behind the magnetic field by 45 degrees. On this page, I want to remind you the field inside a piece of conductor. And if you still remember in electromagnetic 1, I put a positive charge here nearby a piece of ideal conductor. And I mentioned to you that this charge is going to attract electrons toward its boundary and then leave positive charge on the other side of the boundary. And in this process, you're going to build up some internal electric field to cancel out the external field. So if you have an ideal conductor with many charges, then eventually the net electric field inside is going to be equal to 0. So I told you before that the electric field inside a piece of ideal conductor has to be equal to 0. But if you use this conclusion into this Maxwell equation, curl of E equal to the partial derivative of B with respect to t, and then put this E equal to 0 into this expression, then you also have a conclusion that the magnetic field inside this piece of good conductor has to be equal to 0, provided this is the time varying field inside this conductor. So this page tells you that no field can survive inside a piece of good conductor. So everything will happen on the surface. So now we'll be talking about the impedance on the surface of a piece of good conductor. And we are not going to talk about anything inside or deep inside a piece of conductor. So on this page, we'll start to define surface impedance. So think about that you have an instant wave onto a piece of good conductor. And you already know that the electric field and magnetic field will attenuate along the propagation direction. And then within the skin depths, you still have some electric field and magnetic field inside, but not beyond this skin depths. And now, if we allow this piece of good conductor to become a perfect conductor, where your conductivity approaches infinite, then you can see that this skin depth will approach 0. So if we just focus on the surface of this ideal conductor, then you can also define a surface current through this expression, which was derived a long time ago when we talk about the boundary condition of the conductor interface. And so you will be expecting that there's a surface current on top of this. And that is due to the magnetic field on this surface. And the propagation direction of this surface, the current is along the electric field direction. Now, we can just adopt the voltage over current concept to define a surface impedance through this calculation. But turn out that this surface current comes from this magnetic field. So it's equal to the electric field divided by the electric field, just like the way you define the intrinsic wave impedance. So you end up having the same expression as the intrinsic wave impedance of the electromagnetic wave inside a piece of good conductor. And you have the real part and also the imaginary part. And the real part of this surface impedance is called surface resistance. And the imaginary part of this ZS is called the surface reactance. And I want to remind you that in practice, we don't work with perfect conductor. We work with the good conductor. So eventually, the skin depth is not going to be equal to 0, but it's a small value. So this is usually a good approximation. Now, in practice, again, the conductivity is not going to be infinite. And so let me bring out the physical picture again. You have some current flowing on this surface, and the field drop along this direction over a characteristic length called the skin depth. So think about that this piece of conductor is an antenna. So an electromagnetic wave is instant on this piece of antenna. And if you have a field meter right here, you're going to measure some signal from the oscillation of this field. Now, let's run this physical picture backward. You attach this antenna to AC power supply, and then you'll be generating radiation from this antenna and emitting outward. But the physical picture does not change for these two situations. So this means that on the surface of this piece of conductor, you have surface current, but you don't quite have the current inside this piece of conductor. So I want to tell you that when you drive a piece of conductor with an AC power supply, the current tend to be outside the surface, but not inside the surface, because the current inside this volume is not going to generate any radiation. Only the current outside the volume will produce radiation. And so a simple conclusion is that an alternating current power supply drives an electromagnetic wave on a conductor, and the AC current is mostly on the surface of the conductor. On this page, I want to talk about the ohmic loss inside a piece of conductor when this piece of conductor is receiving an electromagnetic wave. Because we care about the loss of the power, because the power is proportional to the resource, and resource is proportional to the money. So think about look into this piece of conductor just like you look into a piece of resistor. So the wave coming down this way, and the electric field is along the x direction, and magnetic field is along y direction. And you'll be introducing a current along the x direction, along the electric field direction. And this direction can be also determined by doing AN2 cross with H. And AN2 is a surface vector along this direction, along the minus z direction. And so you have current flowing in this direction. And then from our discussion about a piece of resistor, you can calculate the resistance according to this formula, where L is the length of the resistor, and S is the cross-sectional area of the resistor, and sigma, again, is the conductivity of the resistor. This L is along the current propagation direction, so in this configuration, this L is equal to delta X. And S is a cross-sectional area. But when you look into this configuration, there's no well-defined cross-sectional area for this piece of resistor, because your current is going to attenuate along this Z direction. But you have a characteristic length that contain the current. So the effective area here is going to be equal to this delta Y multiplying with this the skin depth. So let's put this S equal to delta Y multiplying with delta into this expression, and then replace this L with delta X, which is the length of the resistor. And also you plug in the expression of the skin depth into this expression. Then you end up having this expression. So effectively, the resistance of this piece of conductor is going to be equal to this. And this is equal to this expression, delta X over delta Y, multiplying with the surface resistance. Because on the last page, we already have this surface impedance given by this, and turn out that this plot is just equal to the real plot of this RS. So you just replace this quite complicated expression with RS. Once you have the resistance, then you can use the circuit theory to calculate the power loss. Well, according to the circuit theory, the power loss is going to be equal to this expression. And we talk about the average power loss. So you have a factor 1/2 in front of this I square R. And you have the expression for your resistance. And you have the current inside this resistor. So you do this calculation, you end up having an expression like this. And the reason I give you this expression is that we did the calculation on this page by using a circuit theory, a well-known circuit theory, which is the 1/2 of the I square R. But in fact, I leave it as an exercise to you. You can also do the same calculation and get the same result by using Poynting vector approach. So the Poynting vector wave approach will converge to this circuit theory very well. If you just use the intrinsic wave impedance, and then you know the average power inside a Poynting vector is equal to 1/2 of the real part of the electric field multiplying with the conjugate of the electric field. And then if you go through the calculation and then multiply with the cross-sectional area delta X multiplying with delta Y, you'll end up having exactly the same expression. And this power loss is quite important. Again, it's related to the resource you're going to consume if you propagate a wave inside a piece of conductor. So in this session, I introduced the surface impedance, because for a good conductor or even for an ideal conductor, the surface current and also the electric field, magnetic field are all on the surface of the conductor. So we need to know the surface impedance. And so an electromagnetic wave can only penetrate a good conductor over a small distance called skin depth. The ratio of the electric field to the magnetic field is given by this expression. But when we involve the concept of the voltage to current and define the surface impedance, turn out that this ratio is also equal to the intrinsic wave impedance of the instant wave on the surface of the conductor. And I also explained to you that the current of an AC circuit is on the surface of the conductor, but not inside the conductor. Thank you.